Hello, my name is Heiko and I'm presenting you today dynamic updates of virtual PLCs deployed as Kubernetes microservices. And let's start with a short application example. So we have here a control application for an industrial boiler. So the boiler looks like this. It's a big tank where you can heat some fluids, some chemicals, for example, and it's fed by a pipe, and then you have a valve here and another valve at the output. And then we have a level sensor which measures the level in the tanks. And it sends the filling level, the current filling level, to an automation controller, a real-time controller here. The real-time controller has a control algorithm inside, which it executes cyclically, so constantly every 100 milliseconds, for example. And then it sends the valve opening signals to the valve to regulate the filling level in the tank, depending on the chemical reaction. So the question here is now how to update this control logic without interrupting the production. So what we don't want to have is that we have to shut down this real-time controller, upload a new firmware, and then bring up the whole process again, because that's quite expensive and should be avoided. So we want to do that at runtime. So we also looked into the literature for literature on dynamic software updates, and there are a few works, for example, also for real-time cyclically executing applications, a few older works, but none of these works assumes a container deployment, and because of that they cannot update the underlying controller runtimes and also not the operating system, but they are always restricted to a single node. And then there have been works looking at putting PLC software, these programmable logical controllers, into container environments. Different works here, they essentially demonstrated that the PLC logic can be computed in such containers with acceptable jitter. And finally, there are some newer works on state replication in container orchestration engines, but these are mostly targeting web application, consumer applications, which are not executing cyclically and have usually simpler internal states, like a few client parameters. So our approach is now we want to do the following. So our contribution is that we replace this automation controller and introduce here a Kubernetes cluster, so it's a server host, and run the PLC runtimes as Docker containers inside Kubernetes pods. And that allows us then to spin up an updated virtual PLC, so it can both update the program itself, the runtime, so the execution engine, or even the operating system. It could be a separate node in the cluster. And then we connect the updated engine also to the input signals. And then we do a state transfer, because we need to put the intermediate values from the control algorithms into this updated engine, a state transfer, and we do that via OPCUA, which is a communication protocol on top of TCP/IP. And by that we can also transfer the state between different nodes. And then we switch over the sending of the output signals from the old engine to the new engine, and then we can deactivate the old engine. That's the entire approach. So the parts we need for that is first in Kubernetes. Here's a very short overview on what that is. So you have essentially a control plane to manage different software containers. You have an API server, a scheduler, and a controller manager, and then you have a configuration database called etcd, which takes the entire configuration of the system in terms of which containers and pods, for example, are deployed. And then there are several compute machines which run the actual software containers. Containers are encapsulated in pods, and a pod is a unit of deployment. So if an application needs to run on a single node, then it has a pod with containers in it, and often pods contain only a single container, but it could be also multiple containers. You also have a kubelet and a kube proxy to get traffic here onto those nodes. And then there might be also additionally persistent storage, databases, and a container registry with updated images of the runtime containers. And we can host such a cluster either physically on bare metal or on virtual machines, actually. A private cloud and a public cloud or hybrid cloud. The scenario that we are looking on is more like a private cloud. So we have a small cluster that runs together with your industrial control system on premises, and we can then switch between different pods there. Then we use the OPC-UA communication protocol. So essentially it's a client-server protocol on top of TCP/IP, and an OPC-UA server depicted here. It includes an OPC-UA address space, and the address space contains a lot of nodes. Nodes usually are synchronized with some real objects. It could be, for example, a node for the current level in the tank, or there could be also nodes for the configured filling level in the tank, which is a static value that does not really synchronize with an object. And then OPC-UA clients come in here and browse this address space and read out the current live values, or also the static values that are configuration parameters. You can also set up a subscription so that you get always updated values if a new value is available. And then we also need a PLC engine. At ABB we have commercial PLC engines, but here we decided for the concept of this paper to use an open source engine, and we selected OpenPLC for that. It's an IEC 61131 compliant PLC engine. So this is an industry standard for programming these logic controllers. It has different programming languages included, so there are textual notation and graphical notations. Here is shown an engineering tool with a function block diagram notation, and for example here the fluid level in the tank is connected to a output valve. So this is the logic that is configured here, and here's a less than function block that just regulates the level in the tank. Once you have programmed the logic here, and this is a very simple logic, we have very complex logic in realistic programs, then you deploy the logic to a runtime, and the runtime you can also monitor at runtime while executing, so you see the live updating values, and yeah, can also interact with that. So our architecture looks like that. So we used Kubernetes. So we have here a master node, which serves as a control plane, and then we have different worker nodes. We depict here only 2 worker nodes, but it could be, of course, more than that. But to explain the concept, that's sufficient. What we introduce actually is this virtual PLC operator. And as a prerequisite for that, we deployed the PLC runtimes, the OpenPLC runtime, for example, as Docker containers inside pods. So we have here now the runtime system. The runtime system hosts the PLC program. The PLC program carries an internal state, as for example in the running example was the configured desired filling level in the tank. The program receives OPC-UA signal inputs, so the recent filling level in the tank, for example, from the level sensor, and then it writes the output signals, for example, to the operating valve here. And now the idea here is that this special customized Kubernetes operator, it monitors the running PLC engine, and if a change is detected, for example, an automation engineer uploads a new PLC program into the OPC-UA address space of the runtime, then the operator gets notified and starts the update procedure that we are foreseeing. What it does, it spins up a new instance of the PLC program, a new instance of the PLC runtime here with the updated program inside. And then it reads out the internal state from the existing PLC program, puts it into the new PLC runtime, and then switches over the sending of the signals from the subscriptions here to the subscriptions here. And then afterwards we can deactivate the first engine and then run entirely on the second engine here. And this second engine could also be deployed on a new node that, for example, has an operating system update inside, or has some other changes in there, maybe some hardware changes, something like that. And our approach then allows us to move the executing control program essentially during runtime from one system to the other system. Good. The dynamic flow is like this. We first, once the controller detects an update request, it starts the second runtime, then it connects to both runtimes via OPC-UA, and then it enters a time-critical phase. So we have here steps 4 to 9, and they really need to execute very fast to not lose any execution cycles. I said we have an execution cycle target of 100 milliseconds, and the control algorithms, they need about 10 milliseconds to execute. And so we have 90 milliseconds of slack time. So this step here needs to be completed within 90 milliseconds. And what needs to be done is both engines need to be paused. Then the state gets extracted and serialized, and then sent to the controller, sent to the second runtime, deserialized, and then both controllers are unpaused. And then before switching over the actual control, we verify the correct behavior. They can be either done manually by looking at the outputs that both engines produce, or you can have an algorithm that actually does that and checks for a drift in the output values that has been computed. If that is incorrect, then we roll back everything. If it's correct, then we disable the output writing from the first runtime and enable the output writing on the second runtime. And afterwards, the application is successfully updated. Okay, let's have a look at the short demo now. You see here the Kubernetes dashboard, and we have deployed the OpenPLC engine as a pod here. You see that here as a deployment. And we have also configured a service. So we have an OpenPLC service which exposes a certain port, and via the port we can access a web service which allows us to monitor the OpenPLC engine. And that's what we see here. You see already here there's some live updating values, but actually the parameters are not yet initialized. So we provide a configured upper limit for the tank that this engine is now controlling. And say, for example, 600 centimeters here is the filling level that we want to have. And then the PID loop that's executing here is kicking in and slowly ramping up the fluid level to the desired state. And afterwards it will close the valves again to keep the fluid level at the desired upper limit. Yeah, now we have reached the upper limit, and the output valves are regulated, and you see that they are turning true and false depending on how the fluid level behaves. Now we simulate an update. By that we change the control logic here. We delete a function block, this less than block, and exchange it or replace it with a less equal block. And then we connect the function blocks again. So now we have updated the control logic, and we can compile it again and start another container with the OpenPLC runtime containing the updated control logic. So that's not time critical. You see here now on the dashboard the updated OpenPLC pod, and we put that one here on the right hand side in our demo. So on the left hand side we see the original one, on the right hand side the updated one. You see the updated one has not yet the internal state of the original engine, which is configured for a upper limit of 600. And now we we initiate our Kubernetes operator to transfer the state, and this has been done already, so it's quite fast. And now the updated engine has the same internal variables as the original engine and can continue the execution of the control algorithms. We now switch the actual connection of the updated engine so that it now regulates the valves, and then we can deactivate the original engine, yeah, the production continues without interruption. And then we executed also a larger case study based on a liquid natural gas plant with 18 controllers, which carried up to 100,000 internal state variables per controller. You see a photo here of that plant. We used that just as a template. We didn't deploy our approach already there, but we derived the application sizes from such an application. And now we look at the state transfer time that we achieved. As I said, we had a target cycle time of roughly 90 milliseconds at 100 millisecond cycle time. And you see here the number of variables in the state transfer we used in the experiments in our engine, and then also the execution time of the state transfer. And if you look at the results, 100,000 variables, which was our target derived from the application, could be transferred in 14.19 milliseconds at the worst case. And that is well below our target of 90 milliseconds. So the experiments showed here that it's possible to do the state transfer across different nodes as promised, promised by our approach. So that worked out nicely. We also looked into where the time is actually spent for the state transfer. Good. To summarize, we proposed a new approach for dynamically updating control applications. We introduced a Kubernetes operator to monitor running virtual PLCs, and we can switch between virtual PLCs instances at runtime, and it's very critical to quickly transfer the internal state. And we showed in experiments that it's possible even for large-scale applications, and by that we show that these dynamic bumpless updates are possible for large control applications, which allows us to do the state transfer without any plant downtime. In the future, we also want to add a local shared memory transfer for the state that restricts it then to a single node, but it can maybe even support faster cycle times. We want to enhance the operator so that it automatically selects where to deploy the next PLC engine, the updated engine. And then finally, we also want to look at resource-constrained devices, which are probably not fully integrated in the Kubernetes cluster and need other means to benefit from the container orchestration. Thank you very much for your attention.